Okay, so we're going to try to draw the slope fields for some of the equations that we solved this week. Let's go back to the separable one because this is kind of like one we've already drawn the slope field for. Remember, we can get the derivative by itself. The derivative tells you the slope of the curve at the point, and so for every point in space, we can draw a small slope. And this kind of differential equation only depended on y. So for all values of t, if we go across horizontally, we should see all the same slopes, which we do here. So when y was 0, all the slopes were 0. When y was, see this is 3y, so when y was 1/3, the slope was 1. So we've got these 45-degree slopes here. When y was negative 1/3, we have slope is -1, so this is 45 degrees the other way. And then 2/3, the slope was 2. At 1, the slope was 3, and it gets steeper and steeper as we go up. So we can try, like, for this initial value problem, y of 0 equals 1/3. We can draw this line through, and then there's a little direction line at every point in the plane, but as long as we're kind of parallel to these for every value of y, we're good. So like here, we're parallel to this slope of 3. And we have solution curves going up this way. We have solution curves going down this way. And that those stand for the infinitely many solutions y of the form y equals k times e to the 3t. When k is 0, y is 0. When this is probably, no, k equals 1 would go through here. So that would be a solution curve there. Anyways, each value of t gives you one of these blue curves. And then we can look at the behavior, the end behavior of this, and it actually depends on our initial value. So when y of 0 was greater than 0, right, we're starting up here, then as t goes to positive infinity, then so does y. All these curves up here tend up. If y of 0 equals 0, we're in a special case, we're in the equilibrium solution. So as t goes to infinity, y of t is just 0. You can write tends to 0, but is already 0. And then for y of 0 less than 0, t goes to infinity means y of t goes to negative infinity. All of these go down. Okay, so it depends on the initial condition. Let's look at this next one that we solved, which was dy by dt minus 3y equals 7 e to the 3t. This one you should be able to sketch by hand. This one you may need help. But there are a couple things we can sketch. So, for example, we can ask this question. Where does dy by dt equal 0? Okay, well, let's, we can set that to 0, and we actually get, I don't like writing negative signs out in front, so I'm going to write it the other way. 3y equals negative 7e to the 3t. If I write a negative sign out here, I'm going to lose it on the next line unintentionally. I don't like setting myself up for making mistakes. Okay, so dy by dt equals 0 on this curve. Y equals negative 7/3 e to the 3t. Let's see where that is. So I'm going to have... And this is just going to be a brief sketch. I'm not even going to put numbers on this graph. But I'm going to sketch the curve y equals negative. So e to the power of t looks kind of like that. E to the 3t will grow a little faster. And then if I multiply by a negative constant, I'm flipping it down here, right? So I have some curve that looks like the mirror image of an exponential in the y-axis. And then this curve should be where dy by dt equals 0, which means every little slope line on that curve is going to be horizontal. That's what a 0 slope is. Note that this green line is not a solution curve. Solution curves do not behave this way. If you look up here, the solution curve, every line that it passes through, the slope is equal to the slope of the curve. Here, the slope of this curve, actually, we know how to do calculus on this slope of this curve is never 0, but all the little lines that pass through it our slope 0. Okay, so very important, not a solution curve. Great, so we don't have any solution curves yet. Do we know how to put any other things on here? Well, we could plug in points. For example, this would take all day. This actually sounds fun to me. May not sound fun to you. I'm not going to do it in this lecture because we don't have time. But like, let's say at 0, 0, I could plug in 0, 0 into here. Then I get dy by dt minus 3 times 0 equals 7 times e to the power of 0. So that's 1. Okay, so at 0, 0, my slope is 7. That's actually super steep. What other things can we do? Well, we can ask where is dy by dt greater than 0? And that's actually the same equation, except we solve it. Let's actually write this as dy by dt equals 3y plus 7e to the 3t to make it less confusing. Okay, so this is greater than 0, which means the right side is greater than 0, which means y is going to be greater than negative 7/3 e to the 3t. So everything above that curve has positive slope. Everything below that curve, we can check this, has negative slope. Solve that. This thing is less than 0, so yes, y is going to be less than negative 7/3 e to the 3t. Everything below this has negative slope. And I could check a point. Let's say I check at, let's see, this is going to be negative 7/3. So I could go down more at negative 3, or at 0, negative 3. Then dy by dt, I'm just going to plug into here now, equals 3 times negative 3 is negative 9, plus 7 times e to the 0 is 7, so negative 2. Okay, so I actually did this pretty well. This is about 2 1/3. Okay, so this slope is negative 2. Fairly steep, not as steep as the positive 7 going the other way. Okay, so I've got negative slopes here, positive slopes here. I still kind of don't know how to sketch the solution curves, but luckily I've solved this. Let's see what the solution was. I have y equals 7t e to the 3t plus c e to the 3t. And then I can just put in some values of c. So what I like to do now is just go into Wolfram Alpha or your TI-80, whatever you have, or Desmos or your favorite website, for graphing, and just start putting in, I'll start with like c equals 0, c equals 1, and then what I get are these like really exaggerated exponentials. This is when I do t times e to some power of t. So on the positive side, I get these, didn't do this super well. This should be much closer to this curve. Anyways, I get a bunch of exaggerated exponentials. And then I need to go through these negative things. So these should always be local maxes or mins, or maybe points of inflection, right? That's when derivatives are 0. So what happens is I get these negative things, and then at some point it goes through here, and then it comes back up. And then these are all really close together here, but like sometimes they'll do like a drastic dip and come back up. That's for negative values of c. So 7t e to the 3t minus 8 e to the 3t or something would look something like that. Okay, so that helps us figure this out. Let's look at the end behavior. So it looks like all of these, and this does continue, we have as t goes to infinity, y of t is going to go to positive infinity regardless of the value of c. I don't have cases like I had up here. And we can see that in the equation. Right, because I have a t e to the 3t here, even if c was negative 100, as t goes to infinity, at some point this is going to be positive, a bigger number than 100. And actually I have my 7 here, but even if I didn't, as t goes to infinity, this thing is going to be bigger than this thing. So y is going to go to positive infinity. It might dip down really negative for a while, but then it'll come back up.